The steam methane reforming plant is a production facility that produces high-purity hydrogen by utilizing hydrocarbons and high-pressure steam. Natural gas and C3 LPG, which are primary raw materials for SMR plants, contain trace amounts of sulfur and chlorine and has to be removed in advance to protect the catalysts and other equipment in the later process stages. These contaminants are allowed to react with hydrogen in the hydrogenation reactor, converting them into hydrogen sulfide and hydrogen chloride, both of which are subsequently removed via absorption equipment. The cleaned process gas is heated to approximately 650 degrees and then introduced into a catalyst-filled reformer tubes with steam, where it undergoes the name-giving steam-reforming reactions under the influence of the catalyst, resulting in the production of hydrogen, carbon monoxide, and other byproducts. The reforming reaction is an endothermic process, and the energy required for this reaction is provided through burners situated within the combustion chamber, housing the reformer tubes, and utilizes off-gas from PSA process, and also a portion of the raw material as fuel. The high-temperature process gas exiting the reformer is at approximately 900 degrees and is passed through heat exchanger in the waste heat boiler to produce high-pressure steam utilizing pure water. A portion of this steam is diverted to the reformer for hydrogen production process. Afterwards, the process gas is introduced into the carbon monoxide conversion reactor called the shift reactor, where hydrogen is further produced through the reaction of carbon monoxide and steam, and additional carbon dioxide is generated as a byproduct. As the resultant process gas has high carbon dioxide content and is at high pressure conditions, carbon dioxide can be efficiently separated out within the process gas using a wet method with amine solution. As the process gas passes through the absorption tower and the stripping tower, the captured carbon dioxide is diverted and pressurized by a compressor and processed through purification and liquefaction, resulting in the production of high-purity liquid carbon dioxide. Even after the carbon dioxide removal process, the process gas still contains carbon monoxide, methane, and other components. The resultant gas mixture needs to be further refined via hydrogen purification process equipment known as PSA, where 99.999% high-purity hydrogen is produced and supplied to the end user. When carbon dioxide generated during hydrogen production is captured, compressed, and is safely stored on land or in marine storage via carbon capture and storage process, the produced hydrogen is designated clean hydrogen, making it a viable and sustainable clean energy source, while also contributing to greenhouse gas reduction efforts. In Korea, there is a project underway to store carbon dioxide in the East Sea gas field, and until additional domestic storage options are secured, projects involving transfer and storage of carbon dioxide in abandoned oil wells or gas wells overseas, particularly in Australia and Malaysia, will be pursued. Clean ammonia, supplied through the ammonia terminal tanks, passes through a temporary tank prior to processing. Ammonia is then heated and vaporized before being fed into a distillation tower. In the distillation tower, approximately 0.5% of water contained in the ammonia is separated and drained at the bottom part of the distillation tower, while the purified ammonia vapor is transported into the cracking process via the upper section. The purified ammonia vapor undergoes a temperature increase as it passes through the cracker convection heat exchanger. It is then introduced into catalyst-embedded cracker tubes, where it is decomposed into hydrogen and nitrogen. Ammonia cracking is an equilibrium reaction. Thus, some ammonia exits the cracker in an undecomposed state and accounts for about 5 mol% in the resultant process gas. The fuel source for the cracker primarily comes from off-gas generated in the hydrogen purification process, but clean ammonia is used to supplement any additional heat requirements. Heat generated in the ammonia cracker is recovered via heat exchanger, and resulting heat energy is used to remove the moisture contained in the liquid ammonia feed and supplies the necessary heat in the form of vapor during feeding. The resultant cracking process gas undergoes a cooling process, and the undecomposed ammonia is separated in the process gas separator and returned to the distillation tower, while the process gas is transferred to the hydrogen purification process facility, PSA. The process gas passes through the PSA unit that removes impurities through pressurization, absorption, depressurization, and stripping cycles. The resultant gas is of high purity hydrogen, exceeding 99.999 mol%, and transferred to respective end users while using the PSA off gas is utilized as the cracker fuel. Green hydrogen production technology via ammonia cracking is similar to SMR technology. Leveraging advanced technology and technical collaboration, Aprotium will provide stable supplies of green hydrogen, utilizing our enormously accumulated operational and optimization expertise from SMR operations. Aprotium has ownership of approximately 60 kilometers of hydrogen pipeline infrastructure in the Ulsan area. Through this pipeline network, byproduct hydrogen generated by chemical processes are acquired and supplied to major high-volume hydrogen consumers like SK Energy, S-Oil, SK Chemical, ISU Chemical, and others. Additionally, hydrogen produced in the Aprotium's own SMR plants are directly supplied through pipelines to SK Energy and S-Oil. To ensure the reliability of hydrogen supply and the integrity of the underground pipelines, remote pipeline monitoring and management systems are in place. Furthermore, Aprotium operates a fleet of over 250 hydrogen tube trailers, enabling supply of hydrogen to any location across the nation wherever it is needed. Hydrogen, loaded at high pressure into these tube trailers at the Seosan and Ulsan plants, is supplied to hydrogen consumers covering industries such as semiconductor, automobile, electronics materials, steel, and hydrogen stations. To maximize the safety and efficiency of hydrogen supply, real-time management is achieved through a transport management system developed in-house and is utilized from order receipt to inbound-outbound processes, vehicle dispatch, and understanding customer requirements. In the future, the clean hydrogen produced at the ammonia cracking plant will be supplied through pipelines as a clean energy source to facilities such as combined cycle power plants and fuel cell power plants. Additionally, it will serve as a clean raw material for production processes with eliminated carbon emissions, such as automobile painting factories and chemical plants. Managed through a centralized system with diverse supply sources and optimized production costs, green hydrogen will be supplied to various consumers, including industrial, power generation, and transportation sectors at competitive prices. This will ensure stability and establish a sustainable system for the supply of clean energy.